going to talk about some recent work in this family of methods, both algorithms and analyses, called approximate message passing. This is joint work with Sandeep and Ali, a lot of what I'll be talking about. And I'm going to talk about some of the older work in this area, just in case you guys are not experts, try to set the foundation, and then to also talk about some more recent advances. And there's so much more. I'm just talking about a little piece of it. There's a lot more that I could say, but in the interest of time, I'll have to be a bit brief. And I'm sure I'm going to leave out a lot of interesting things and contributions from other people in the audience here, but I'll do my best. Okay, so I'll start focusing. For most of this talk, I'm going to focus on the problem of linear regression. And I'll talk a little bit at some point about bilinear, but mostly linear. And then I'll focus on different approaches to think of this problem, whether you think about it from an inference perspective or an optimization perspective or a deep learning perspective. And I'll try to tie all these things together. So just to start out with the problem setting and notation here. So we suppose that we've made some measurement y. Y is a vector of m real numbers. And we suppose that there's some signal, x naught, that we're trying to recover that is seen through the application of some linear transformation A. And we see it in the presence of additive white Gaussian noise, so independent Gaussian noise. And we know A. Obviously, we don't know the noise. We don't know the signal x naught, which we're trying to recover. So one of the most well-known approaches to this problem is to formulate it as an optimization problem, where we minimize the sum of a term that we can think of as a loss function, or you could say as a negative log likelihood, plus some sort of regularization term, and that regularization term, or penalty term, penalizes some unlikely signal realization. So basically, let's say we know a priori that our signal is sparse, then maybe we put in a sparsity inducing regularizer here, like L1, the L1 norm. This regularization term here, maybe it's telling us about, maybe it's inspired by a prior, but maybe that prior has some unknown parameters. So for example, maybe we're talking about sparsity, but we don't know how sparse. So there's a vector of parameters theta 1, which is somehow, this is going to be associated with the signal model. For the beginning part of the talk, I'm going to assume we know this, and later I'm going to talk about jointly estimating these hyperparameters theta 1 and theta 2. So here theta 2 would play the role of a noise precision. So if you know, or you posit that your measurements are observed in additive white Gaussian noise, but you don't know how strong that noise is, theta 2 would be the precision or the inverse variance if this is the negative log likelihood. Okay, so optimization, otherwise known as map estimation, would be one approach. Another approach is to treat it as an approximate minimum mean squared error problem. So in this case, we're interested in computing the conditional mean of x given y. And here we would associate x with some prior, and the likelihood y given x would be the likelihood here. And again, so theta 1 and theta 2 are some unknown hyperparameters of the prior and of the likelihood. So those are probably some of the most well-known approaches. More recently, especially in the field of image processing, there's an approach where that exploits the fact that people have worked very hard on the simple denoising problem. The denoising problem is essentially like the first two, but with the A matrix replaced with an identity. So you observe a noisy version of the signal, and you somehow just want to recover the signal without the noise. So for image processing, this is a whole cottage industry. There's hundreds, maybe more, papers on this, and one of the famous algorithms is BM3D. And it's been proposed to put this inside some iterative algorithm, and this actually works incredibly well. So this is another approach we might consider nowadays. And finally, we might also consider the very modern approach of training a deep network to recover the signal directly from Y. Maybe that network is not even told the A matrix. Maybe it's just given a lot of training examples, pairs of X and Y, and then given a new Y, it tries to reconstruct the X. Okay, so the way that I'm going to be tying these together is that basically this approximate message passing framework can just sort of is linked to all of these, or can be linked to all of these. And these different approaches are tied together through this idea of iterative denoising. And in particular, they differ in how you define the denoiser. So if we want to solve an optimization problem, then as many of you are probably familiar with iterative optimization algorithms, things like ADMM, they often use this proximal operator, which is basically this map denoising problem here. And so when you look at algorithms like ADMM to solve this sort of linear regression problem, they keep calling this proximal operator, and what changes throughout the iterations of the algorithm would be that R vector. Another way of building a denoiser is to build a minimum mean squared error denoiser. So that would be the conditional mean of x given R. R is a noisy version of the true signal. In the plug-and-play case, we would use some extensive knowledge of the signal class, like the fact that we're dealing with natural images, and we would maybe build some very complicated black box denoiser like BM3D. Or in a deep network, we would somehow learn the structure of the thing we're trying to extract from seeing many, many training examples of it. Okay, so I'm going to start now back to the just sort of simplest case. This is the original AMP algorithm. Let's see, so there should be a, okay. So I somehow left out, so this is proposed by Donahoe, Malecki, and Matsunari in 2009. Although there's a lot of prior work on similar stuff in the statistical physics literature, maybe slightly different forms of it. But basically the idea of the algorithm is if we forget about that blue part, then this looks very similar to what we call the iterative thresholding algorithm, where this VT is, so x hat t is your approximation of the signal you're trying to recover at iteration t, and then y minus ax hat t would be the residual, so that's the error that you see from y. And then basically you can multiply that on the left by A transpose to bring that back to the signal domain, put that through your denoiser again, and repeat this process. So this is a very famous algorithm that's been around for several decades. What was new, proposed by Donahoe, Malecki, and Matsunari, is to add this blue term here, which is in the physics literature called the Onsager correction term. And this sort of works magic in the algorithm. The algorithm works a lot better than before, but what's maybe more interesting for the information theory perspective is it gives us a way of predicting exactly what's going to happen. It gives us a way of understanding in a certain large system limit exactly how things will behave. And I'm going to get into that in just a moment. So from one perspective, we can think of taking this standard kind of old-fashioned algorithm and adding this correction term. You might ask, well, how exactly do you formulate this term? There's different ways to derive it. One constructive way is to use the idea of belief propagation on a factor graph. Here, the way that we construct the factor graph is so those x1s are the scalar signal variables. The black boxes to the right would be the prior distribution, and then the black boxes to the left are the likelihoods. And essentially, you pass messages around this graph. That's what loopy belief propagation says. But if we make some simplifications and we just pass Gaussian messages instead of passing PDFs, we just have to pass means and variances. We make some further simplifications, and all of a sudden, we get this very simple two-step algorithm. So I don't want to say too much about that. There's different ways to arrive at it, but what's more interesting is what we can finally say about this algorithm. So if we say that this matrix A is IID sub-Gaussian, if we say that the dimensions m and n of this matrix grow together at the same rate, so that overall the ratio converges to some number delta, some positive bounded number delta, and if we say that the denoiser is separable in the sense that every coefficient of the denoiser is identical. So basically, the denoiser acts identically on every coefficient of R by some scalar function g. And we're going to assume that the scalar function g is Lipschitz. Then we can say something quite remarkable about what happens to the input to the denoiser. Basically, the jth coordinate of that input vector is the true signal, the jth coordinate of the true signal we're trying to recover, plus this Gaussian noise. And once we see this, we can now understand why we're thinking about this G function as a denoiser, because once it's placed inside this AMP algorithm, its job is simply to denoise. It's given R, it wants to produce X. There's different ways you could do this. You could, again, formulate this as a proximal operation if you want to think of it as solving an optimization problem. If you want to solve an MMSE inference problem, you would use the scalar MMSE denoiser. And, but this is the remarkable feature that happens with this correction term. Without that correction term, what happens is, in general, it's very messy, it's very complicated. There's certain sort of errors that build up over the iterations. It's very hard to say what's going on. But you put in this term, and all of a sudden, it's incredibly clean. And so this is what's so interesting about these AMP algorithms. And starting from this, we can go further. Oh, there's one other thing. So the noise variance here, what I'm calling tau r, this changes with the iteration t, but this also can be easily predicted. So this is one of several heuristics that we can use to predict this. This v was the measurement residual. And under these assumptions, this estimate also converges to the true value. So basically, with just 3 lines, we have this algorithm that is very predictable. We know exactly how it's going to behave. And so let me get into a few more details now about what we can say from those predictions. So let's assume now that the measurements y were actually generated from some true signal x naught by multiplication of a and then addition of some Gaussian noise with variance tau w. And we're going to assume that this vector of entry is x naught. We can think of it as a deterministic vector. We can think of it as empirically converging to some random variable capital X naught as the dimension increases. And if we define the mean squared error as the difference between the true signal vector and the estimate at iteration t, Euclidean norm squared, divided by n, then this mean squared error obeys this extremely simple recursion. So essentially what we have here, the input to the denoiser, again, is the truth plus Gaussian noise. For whatever denoiser, as long as it's Lipschitz, we can perhaps characterize this. What is the output? How does that differ from the true signal? Square that, that's the mean squared error. So basically, we have a scalar recursion here. We have, in reality, a high-dimensional inference problem, but it boils down to a simple scalar recursion. The next time around, the noise variance that's affecting the input to the denoiser is just the measurement noise variance plus some ratio of the previous mean squared error. Okay, so this is a very clean, easy to understand description of what's going on in this high-dimensional inference problem. So now we might ask the question, is this algorithm going to give us a good answer? And what's interesting is that in certain regimes, it actually gives us the Bayes optimal, the minimum mean squared error estimate. So in particular, if we assume now that the vector we're trying to recover contains IID draws of some random variable x naught, and we build our denoiser in the minimum mean squared error way, so using a conditional mean. We also assume that the denoiser is assuming a noise precision which is consistent with the truth at that iteration. Then if this state evolution has a unique fixed point, then we know that the estimate actually does converge to the MMSE estimate as the iterations go to infinity. Okay. Now, it does not always have a unique fixed point. In a very difficult problem regime, it won't, there will be a difference between the true MMSE estimate and what AMP gives us, but in a sort of easier problem regime, AMP will give us the optimal solution. Okay, so just to sort of summarize a bit, so what's good about AMP is that with these large IID sub-Gaussian matrices, this algorithm is characterized by rigorously characterized by a scalar state evolution whose fixed points, when unique, are Bayes optimal. And even though I've been focusing on the case where the dimensions grow to infinity, Cindy and Ramji have done some really nice work to show that even at large but finite sizes, basically similar stuff happens. So empirically, okay, so what about in practice? So empirically, we're not working necessarily with Gaussian, IID sub-Gaussian matrices. We're maybe trying to solve some problem. The matrix was given to us. We can't guarantee that it was drawn in this way. Well, in practice, you find that in most cases, when this matrix is, let's say, sufficiently random, for example, randomly subsampled Fourier, things work out fine. But it's not always the case. So one of the problems is in practice, we lose these theoretical guarantees. We don't really know how it's going to behave. And then in the worst case, sometimes we're given an A matrix in some application for which the algorithm just diverges. So it's completely useless. So this sort of, these issues motivate us to try to go further and say, can we somehow robustify the algorithm or maybe come up with a different algorithm that is somehow more robust? So in response to this, we've done some work which we called vector AMP. I'll describe why we call it that in a moment. But basically, it's very, very similar to AMP in terms of what you get. The algorithm itself looks different, but it's very similar with what you get, but it handles a larger class of random matrices. So again, our objective is the same. It's recovering this signal x naught from some measurements y equal a times x naught plus Gaussian noise. And what we're going to assume now is that the matrix is right orthogonally invariant. So what we mean by that, one way to think about it is you take an SVD of this matrix, and in this SVD, the left singular vector matrix can be deterministic. It's obviously orthogonal matrix, but it can be anything. It could be identity, doesn't matter. The singular values are also deterministic. We don't really care what they are. But this right matrix, orthogonal matrix V, this should be drawn uniformly on the set of orthogonal matrices. So this is where the randomness comes in. This is so-called hard distribution. And one special case of this model is IID Gaussian. But IID Gaussian basically tells us that we should expect a very prescribed ratio of these, or prescribed distribution of the singular values. This is more general in that we can handle essentially any singular values you want. The algorithm itself, you can again derive it by some message passing techniques. Instead of loopy belief propagation, in this case it's expectation propagation. When you draw the factor graph, rather than dealing with the scalar components of the vector, you deal with the vector as a whole, and so you pass vector messages. And for that reason, we called it vector AMP. But basically, in some forms, it is an instance of EP. Otherwise, it's a bit more general than EP. Okay, so the algorithm itself, there's more than 2 lines, more than AMP. So let me just try to kind of lead you through it. So at a high level, there's 2 very symmetric parts to the algorithm. The first half is doing some denoising of our signal according to the signal model. So this is exactly the same G function that we saw before. So for example, if we're in the simplest case dealing with something like we're trying to solve the lasso problem, trying to do compressed sensing, then we would choose G1 as a soft threshold. But we can be much more sophisticated than that if we like. The second half of the algorithm is doing a linear minimum mean squared error estimate. So basically what it's trying to do is it's trying to recover x from this model, assuming that x is Gaussian with a mean R2 and a covariance of identity divided by gamma 2. So this, the optimal mean squared error estimate here is linear. And if you do this SVD in advance, you can write it in a way that doesn't, so there's an inversion here, but it's an inversion of a diagonal matrix. So this boils down to 2 applications, 2 matrix multiplies. In this sense, it has the same complexity as the original AMP algorithm. These other 2 steps are doing some sort of Onsager correction. They take the output, they subtract something intuitively to decorrelate what happens as the iterations progress. And the rest of these terms, eta, gamma, and so on, are some scalars. And these lines in between say exactly how we set them. I don't want to get too much into the details here. But yeah, so the algorithm is not as simple looking as the original AMP algorithm, but conceptually it's not really too much different. Okay, so what can we say about this algorithm? So here we have assumption 2. It's very similar to the previous assumption for AMP, except that rather than A being IID Gaussian, we say it's right orthogonally invariant. So it has, it's a random matrix whose distribution is invariant to right multiplication by any fixed orthogonal matrix. We have the same large system limit. We grow the size of this matrix. Both dimensions, at the same rate. And we have, again, the same assumption on our denoiser, that it's separable. And we find, once again, the same property, that the input to this signal denoiser is the truth plus additive white Gaussian noise. And we have, again, this interpretation as a denoiser. And we have different ways where we can construct the denoiser for solving optimization problems, or for solving inference problems, and so on. Okay. Then we can go further and we can define the state evolution. So this is a scalar state evolution that tells us exactly how the algorithm should behave over the iterations. A few more lines than in the AMP case, but pretty intuitive. We're tracking 2 different mean squared errors, 2 different divergences, and 2 different noise precisions that interact, but it's a scalar recursion. And what can we say about the Bayes optimality now? So again, we're going to assume that x naught is IIDs of some random variable. We choose our denoiser in the MMSE sense. And if, again, the state evolution has a unique fixed point, the mean squared error converges to the replica prediction of the minimum mean squared error as the iterations go to infinity. We would like to say that it converges to the minimum mean squared error, but as far as I know, this problem has not been solved yet. So for this class of matrices we're considering now, which is right orthogonally invariant, the replica prediction was derived by Giulino, Caire, Verdu, Shamai in 2013. That replica prediction is using techniques from statistical physics. It's conjectured to be correct. In some special cases, like IID Gaussian, it has been proven correct recently, but as far as I know, the general case is still open. Is that right? Yeah. So, okay, but it's believed to be correct. So when that's proven, I think we'll see that this vector AMP algorithm converges to the MMSE solution whenever this state evolution has a unique fixed point. Okay, so here's just sort of a numerical example to give you guys a sense of the benefits of this. So what we've done here is we've constructed this A matrix in such a way that along the horizontal axis, it gets progressively worse in terms of its condition number. So in this first case, the singular values all have the same level. And then as we go to the right, the singular values, they have this exponential decrease, and it just gets sharper and sharper. The replica prediction is this dashed black line on the bottom. We expect that as the matrix gets more and more ill-conditioned, the performance mean squared error to get worse. The vector AMP algorithm is doing a great job of tracking it. This little gap over here is due to the finite dimensional regime. So the theory says that in the large system limit, the gap closes, but here we're only looking at 10,024 elements. It wasn't enough in that regime. But then down here we have what happens with the standard AMP algorithm. It works fine when the matrix is well-conditioned, but as soon as it gets a little bit ill-conditioned, AMP diverges. So does this S-AMP algorithm. With some heuristic damping techniques, we can get it to work a little bit better, but at some point those stop working too. So this is one of the advantages of this Vamp algorithm, and it helps us extend these approximate method passing techniques to a larger class of matrices, such as ill-conditioned matrices. So this shows for very well-conditioned and not so well-conditioned matrices, it shows mean squared error versus time. One thing I want to highlight, here we have a realization in blue, and then the state evolution prediction in black. You can see they're tracking together very well. So this is, again, to reinforce that one of the nice things about this class of algorithms is that we can predict what's going to happen exactly at every iteration in the large system limit. And at least for this case, 1,000 is large enough to do that prediction very well. The other curves show what happens with the other algorithms. So one point is that this vector AMP algorithm is a little bit faster than AMP for well-conditioned matrices, and for ill-conditioned matrices, AMP just diverges. So I think I clipped the mean squared error at 0 dB, but actually it gets worse over the iterations. So now, until now I've been focusing on more of a random signal models. What about these optimization problems? If you say, okay, I just want to solve this problem. I don't want to make any assumptions about my matrix A. Is this algorithm still useful? What is it going to do for us? So this is the problem we want to solve. Let's assume that this regularizer here is strictly convex. So, and we're going to choose the proximal, the prox denoiser, as usual. And there's, if you remember in the algorithm, there's one scalar damping coefficient that we can choose. If we choose it in this way, we can prove that this Vamp algorithm, or a slight modification of it, converges to the solution of the optimization problem for any deterministic A matrix. So this is one nice outcome of Vamp. We tried for years to do similar things with the original AMP algorithm. We could never do this outside of some special cases. So we're able to do this with the Vamp algorithm, which is nice. Another connection to the traditional optimization literature is if you fix these, you can think of them as step sizes if you like, fix these gamma 1, gamma 2 variables over the iterations, then the Vamp algorithm reduces to a variant of ADMM, which is known as a Piesman-Ratchford variant, which is basically like ADMM with 2 dual updates. So what Vamp does differently is it's trying to furthermore optimize these step sizes as well, whereas the traditional ADMM just leaves them fixed. The user has to choose them. Okay, and here's an example of this Vamp and AMP and a couple other popular algorithms from the convex optimization literature. Here, our objective is to solve this lasso problem here. And on the left, we have an example for what happens when A is an IID Gaussian matrix. So the rightmost curve is the famous FISTA algorithm, probably one of the most well-used algorithms for this problem. It takes a couple hundred iterations to converge for this realization. Then we have the Chambol-Pock algorithm, which is a little bit more modern and, again, very popular algorithm. It takes maybe about, 80 iterations or so. The AMP algorithm takes about 20, and Vamp maybe about 12. So, so this is solving lasso. Now this is with an IID Gaussian matrix. If we put in a matrix that's not IID Gaussian, or what I'm going to do is I'm going to correlate the columns. Then AMP diverges completely. The other algorithms slow down. They take more than 1,000 iterations. And the Vamp algorithm slows down a little bit, but still is much faster. Yeah.
Seems like if you know when to stop FISTA, you could do better.
Oh, yeah, right. So I'm showing the mean squared error here. That's something you don't know in practice. I could have also plotted like this cost, but that you can evaluate. But yeah, this ringing behavior, I don't know exactly, when that happens. It's sort of like there's a MMSE solution. It's sort of overshooting it, and but yeah, I don't know. You could do a little bit better, but okay. Okay, so one of the nice interpretations of the algorithm, and which is useful from the point of understanding it, and also useful for the point of finally saying what do we do if these hyperparameters theta 1 and theta 2 are not known, is through the variational inference framework. So here the idea is we would like to compute this exact posterior. This is the ideal thing we would like to compute if possible. Now this turns out to be not possible in practice, but if we could compute it, the form of it is a prior. This is a prior in a signal times a likelihood term. So until now, we've been assuming that the likelihood is Gaussian, but just for notational compactness, I'll write it with an L. And then we have some scaling factor, the partition function, which is some high-dimensional integral. And so we know the prior, we know the likelihood, but the scaling factor, we don't know that value, and we don't know exactly how to compute it in any efficient way. So we might say maybe there's something we can do just to circumvent needing to compute that. So for example, what we could do is we could simply say, all right, why don't I hypothesize some belief? So this is a density B, and I want to find the belief that is closest to my posterior, and closest in the sense of KL divergence. So obviously that is the posterior itself without any further constraints. Okay, and now let's go one step further and let's plug in that posterior into this KL expression. And we find that this splits into three terms. There's the divergence from the belief to the prior, plus the divergence from the belief to the likelihood, plus the entropy on that belief. And in statistical physics, they call this the Gibbs free energy. And this is going to show up a little bit later. So again, this is not a very easy problem. Why don't we try to split this into three separate problems? So why don't I just do, similar to variable splitting in the optimization literature, I'm going to do belief splitting. So I'm going to split my belief, just call it three beliefs now, belief 1, belief 2, and something called Q, which is another belief. And so the problem I would really like to solve, in that problem, these are all identical. But if I didn't have this constraint, the problem would be very easy to solve. I can, obviously I know that the belief closest to the prior is the prior itself, and so on. But the point is that they're coupled together. All these problems are equally difficult as the original one. Okay, but for the purpose of moving forward, we're going to call this cost function here the Gibbs cost, and it's a function of three beliefs, as well as the hyperparameters of the prior and of the likelihood. We'll call those theta. Okay, so this is the problem we would like to solve, but none of these techniques are really practical. So a technique that is practical that was proposed in 2004 is called expectation consistent approximation. So the idea here is to relax this equality among the densities to moment matching among the densities. So we want to find the beliefs that are consistent in terms of their means and maybe in terms of their covariances, or something simpler, maybe just the trace of their covariances. So in this case, this is solvable. What we can do, at least we can figure out what the stationary points of this cost are just by standard Lagrangian formulation. And I'll skip the details, but what you find is that the beliefs have a very interesting form. So the first belief is a product of the prior times a Gaussian. The second belief is a likelihood times a Gaussian. And the third belief is itself Gaussian. And again, we need consistency in the means and consistency in the traces of the covariances. So essentially what we have to do now is we have to try to find these parameters. So this is vector R1, vector R2, scalars gamma 1, gamma 2, eta, and a vector x. And so the question is how to do this. One approach to do this is the famous expectation propagation algorithm. It doesn't give you any guarantees about whether it converges to this particular solution. But essentially, this is what Vamp is doing. It is essentially estimating these pairs one at a time as it iterates through the algorithm. And this is sort of another viewpoint on what it's trying to solve. And so you could say, at the end of the day, it is trying to solve some constrained optimization problem, minimizing Gibbs free energy subject to these moment matching conditions. What's of course interesting is that with large random matrices, where the algorithm is going becomes finally analyzable. But the reason I'm interested in this is we can actually use this Gibbs formulation to solve the problem of how do we estimate the hyperparameters jointly with recovering the signal. And the idea is to go back to the classical expectation maximization approach. So in expectation maximization, what we do is we try to maximize the likelihood or minimize the negative log likelihood. But to make this tractable, we add a term that gives us basically an upper bound on this negative log likelihood, and we optimize that and iteratively improve our upper bound. So this is I would say the standard formulation, the standard way we think about EM. But what's interesting is that we can actually rewrite the EM algorithm directly in terms of this Gibbs free energy that we see on the previous page. So here, what we're doing is we're updating our beliefs at every iteration of EM, but we're optimizing over those hyperparameters theta. Whereas on the previous page, what we were doing is we are fixing the parameters theta and optimizing the beliefs subject to these moment matching conditions. Okay, so we can basically put these two things together. So we can basically interleave expectation maximization and Vamp and say we have this Gibbs free energy. let's minimize over the parameters and the beliefs subject to these moment matching constraints. And this gives us an algorithm which is almost identical to this original Vamp algorithm, but it has two steps, which are the EM steps, where we basically, maximize the expected log likelihood. So, so again, this algorithm at the beginning seems heuristic. Yeah, maybe it works, but what's interesting is that we were able to prove a rigorous state evolution for this algorithm. Again, when the matrix is large and right orthogonally invariant, the prior is IID. And so with a slight modification, which we call adaptive Vamp, we can even prove something stronger, which is that the hyperparameter estimates actually are consistent and that they converge to the truth over the iterations, as long as the prior satisfies some identifiability conditions. So, for example, it's in the exponential family or finite cardinality. And basically what this adaptive Vamp does is, rather than this simple EM update, it says don't trust the precisions gamma estimated by Vamp. Estimate those along with the parameters, and this is more robust. So this is where we finally get the consistency out of this. Okay, so here's returning to a figure I showed you earlier. Vamp is the blue trace. It's still shown. It's kind of hard to see. And now what we said is, let's suppose I don't know the signal sparsity. It's a Bernoulli Gaussian signal, but I don't know the sparsity rate. And I don't know the noise, the additive white Gaussian noise measurement noise variance. Can I learn these and do as well as if I knew them, if a genie told me them? And the answer is yes. So this EM Vamp is the red curve. As you can see, it's right on top of the blue. And so somehow we're able to estimate these hyperparameters and recover the signal, even as a conditioning of the matrix gets bad. Previously, we tried to do something with the AMP algorithm, and that works quite well for well-conditioned matrices, but then eventually it falls apart. Okay. So, all right. And then in terms of how much does this slow us down over the iterations, you can see it's not much. It's just like a half an iteration cost to estimate those parameters, those hyperparameters. Okay. So how much time do I have? 10 minutes. Okay, great. So, so now moving on to another extension we've done recently is, so if you remember, there's this denoising function G1. Its objective is to recover some signal x0 from a noisy version, a noisy measurement or pseudo measurement of that signal. And until now, we focused on denoisers that are separable, and that G function operates individually on every one of the entries of R in exactly the same manner and in a scalar manner. But as we mentioned at the very beginning of the talk, there's, for example, like in image processing, people have developed some very sophisticated denoising algorithms which do not operate in a scalar manner. They're not separable. Things like BM3D or DNCNN is a deep network approach to image denoising. So can we somehow plug these things into the AMP or Vamp algorithm and actually exploit the work in that field? They should work much better than a simple sparsity-based denoiser, and they do. But can we say anything theoretically about this? What do we expect can happen? One other practical issue is how we measure this term, the divergence. So this is basically the trace of the Jacobian. So this is something that for simple scalar denoisers we can do in closed form. For these black box denoisers, we can use this Monte Carlo trick. It seems to work quite well. We basically we call the denoiser twice. First is on the original R vector. Second is on R plus a small random perturbation in some random direction. And basically with those two, we can get an estimate of the trace of the Jacobian. Okay, so yeah, so basically for these vector-based denoisers, we have been able to extend some of the theory behind Vamp. There was earlier work by Berthier, Montanari, Nguyen in 2017 that did the same for AMP. And let me show you sort of an interesting application of what you can do with this. So until now, I've been focusing on linear regression problems, but here's a bilinear regression problem. So let's say that the matrix is composed of a linear combination of known matrices phi, but let's say that the combining coefficients b are not known. So I don't know the b coefficients, nor do I know the vector c, which I'm trying to recover. So for example, this shows up in calibration problems where b might be some calibration parameters in your forward model. So what we can do is we can so-called lift this bilinear problem into a linear problem by rewriting it this way. We come up with a bigger matrix where we stack those phi matrices, and we collect the b coefficients into a matrix, and then we have here the vectorization of this rank 1 matrix. We can call that vector x. And now we have taken this bilinear problem, reformulated it as a lifted linear problem, but now you can see that the signal has an interesting structure. The signal x is a vectorized form of a rank 1 matrix. So now in order to recover this, I would like to exploit that rank 1 property with an appropriate denoiser. Okay. And so if we do this, this works, and we can prove a state evolution. Here's just an experimental validation of the state evolution. You can see the vector amp algorithm is tracking it more or less perfectly. And these are some results comparing to some other algorithms. Again, I'm looking here at what happens as the matrix gets worse, the condition number gets worse. So the Vamp algorithm, or what we call Vamp lift, is most robust. There's some previous work with Scalar amp bilinear that is not robust to this ill conditioning, and then some sort of a non-convex optimization, WSS-TLS, which is not doing as well either. But I think it's really interesting that we can predict exactly what's happening here. And finally, just in the last few minutes, I'll talk about connections to deep neural networks. So basically until now in the talk, we've been focusing on this approach where we build an algorithm to recover a signal x given measurements y. To design that algorithm, we tell the algorithm what we know about the signal model and what we know about the forward model, like our forward operator A. So a very different approach is to say, I just have a whole bunch of training examples, pairs of x and y. I'm just going to learn the relationship from y to x, and then given a new y, I'll just predict the x that corresponds to it. Okay, so different approach. Are there connections between these approaches, and are there connections to these AMP methods? And so that's what I'll talk about next. So one thing we could do, for example, let's just take this very classical iterative soft thresholding algorithm. So here G is a soft thresholding function. This solves the lasso problem. We can rewrite this as a one-line recursion using a pair of new matrices S and B. And then we can unfold it. We can draw it as a block diagram if you like. Each one of these sections would be one iteration of the algorithm. And so running, let's say, 3 iterations of the algorithm would be basically putting y through this network. Out comes our estimate. So based on this idea, Gregor and LeCun in 2010 said, well, okay, maybe we can learn better matrices B and S than the ones that are given to us. And we'll just learn them by treating this as a neural network. We'll throw tons of data at it and run back propagation. And in fact, this works really well. We had the idea, well, AMP is just like ISTA with an extra Onsager cancellation. So can we just put that Onsager cancellation here into this network? And it kind of looks like this. So this is one way of writing one stage of the LISTA network, the learned ISTA network. And if we put in that Onsager cancellation, we're just putting in a few more branches, if you will. And the objective of the Onsager correction now would be to decouple errors across layers of our neural network. Okay, so how well does this work? So here's an example of mean squared error versus either layers or iterations, however you want to think about it. So starting at the top, we have the ISTA algorithm. This takes thousands of iterations to converge. FISTA takes hundreds. AMP takes, for this problem, maybe about, 30 or 40. LISTA is actually better than AMP, converting faster, but learned AMP, so it's like Lista, but with the Onsager correction, is doing quite a bit better. And this QQ plot is verifying that we indeed have Gaussianity of the variables inside the network, and this is what we hope for in these AMP algorithms. Okay, so we call this LAMP algorithm. So now, until now, we've focused on soft thresholding, just because Lista uses soft thresholding as its denoiser. So to be fair, everything here is soft thresholding, but why stop there? Perhaps we could do something more sophisticated. So maybe I can learn the denoiser as well. So here's various models, like exponential kernels, piecewise linear splines. These have adjustable coefficients, which we can learn. And what we find is when we do this, we have a big improvement. So here's Lista, LAMP with iterative soft thresholding, and then here we have splines, piecewise linear, and so on. So we get significant improvement here. So we were very excited. We said, that's great. And at the same time we were doing this, we were working on Vamp, and we said, let's compare this fancy learned network, which took us a whole week to train on TensorFlow. Let's just compare that to our simple Vamp algorithm. We were expecting it to do better, but sort of surprisingly, this Vamp algorithm was winning. So, okay. I said, well, maybe we can improve Vamp. We'll try to learn Vamp. We'll unfold Vamp into a deep neural network. And now what we have is this S matrix is basically this linear stage of Vamp. And then the G is it's the denoiser. We'll take the same approach. We'll train TensorFlow for a week, and we'll optimize these. We'll learn a better denoiser and a better linear stage. And what we found is actually we start with a random initialization, and we learn the Vamp algorithm. So it learns to use the linear MMSE denoiser, and learns to use the scalar MMSE denoiser here. So when we thought about it, of course, that makes sense. But it's kind of a nice example of theory coming around and saying, yes, we're doing all this learning stuff, but if the problem is at least simple enough to analyze, then we should get something that makes sense. So, so that was kind of cool. So basically, yeah. So essentially what's happening here in this Vamp algorithm is that what it's doing essentially, it's taking this big kind of global problem and it's breaking it down into stages which are simpler problems, but it's still optimal in those simpler problems. So the simpler problem is recovering a Gaussian vector from some matrix measurements, or recovering a non-Gaussian vector in additive white Gaussian noise. Those are the simple problems we know how to solve. Vamp puts them together in this bigger algorithm that does the overall global minimum mean squared error result. Okay, so just to wrap up then. So AMP and Vamp are both computationally efficient algorithms for linear regression. Vamp is a bit more robust in that it handles a wider class of matrices, in particular these large right orthogonally invariant matrices. What it gives us for those matrices is a rigorous state evolution whose fixed points, when unique, match the replica predictions of the MMSE. Even if we don't have these large random matrices, we're solving a convex optimization problem, we can still say nice things about the algorithm being provably convergent. If we're solving some sort of inference problem where we have priors and likelihoods with unknown parameters, we can learn those as well by combining Vamp with EM. If we have complicated denoisers that are not scalar but plug in things like a deep neural network that itself is a denoiser, we can plug this into the algorithm and we can still analyze it rigorously. We can also unfold the algorithm into a deep neural network, and we try to improve it. It's already optimal. And there's many, many things I didn't discuss. Generalized linear models, multi-layer approaches, bilinear approaches, but yeah. Anyway, thanks for listening.